On the right-hand side of the screen, you can see a solenoid, which is hollow in the center and consists of wrapping a copper wire many times around that opening. The two ends of that copper wire are connected to the ammeter on the left, which starts off as reading 0. When I press play on the video, you're going to see that I approach the top of the solenoid with a series of magnets that essentially behaves like a bar magnet. And when that series of magnets gets to the top of the magnet, I'm going to push the magnets into the solenoid. And when that happens, you see that the current jumps or spikes to the left. And soon, when I pull the magnets out, it spikes to the right. And now, when I approach the solenoid more slowly, you can see that the current red is to the left as it's going in, but it's not as big. And when I pull the magnets out more slowly, coming out, the current is still to the right, but not as big. And now what I'm going to do is I'm going to take the magnets off and flip them. At the beginning, you might have noticed that there was a little rubber band attached to the bottom. Now that rubber band is on the top. And now you should notice that when the magnet goes in, the current is red to the right, and when the magnet comes out, the current red is to the left of 0. My goal in this video is try to explain some of what's happening with the magnets and the solenoid and the current that's being read by talking a little bit about magnetic flux and Faraday's law of induction. In order to understand what's happening, we need to take a closer look at the magnet. So let's assume that the magnets that I have simply act as a single bar magnet, and maybe the north end of that bar magnet is at the bottom, and the south end of that bar magnet is at the top. If that were the case, then the magnetic field lines around that bar magnet might look something like this, where those magnetic field lines would come out of the north pole of the magnet, wrap around to the south pole of the magnet, and then travel through the magnet from the south pole to the north pole, forming continuous loops. And so if I were to only draw a subset of those magnetic field lines, they might look something like that. And now what I want you to do is imagine a circular loop that has nothing to do with the magnet or the solenoid or anything else, just a circular loop that you're imagining, and I want you to imagine placing that circular loop near the north pole of that magnet. When it's very close to the north pole of the magnet, you should see that most of those magnetic field lines that I've drawn are running through that loop. And if I were to take the loop and move it away to, say, here, you should see that at that location the magnetic field lines are more spaced apart, and that's an indication that the field is weaker there, and so fewer field lines would run through the loop. The orientation of the loop is the same there, but less magnetic field, we might say, is going through the loop. And this is the idea of magnetic flux. The quantity on the left, which is read as phi b for the magnetic flux, is defined by a couple of different variables. The first of those variables is the letter A, which here represents the area, the cross-sectional area of that loop. And so in this particular case, you could use pi r squared to find the area of that loop, and the area would be measured in meters squared. B represents the magnitude or the strength of the magnetic field that is going through the loop, and that would be measured in Tesla. And theta represents the angle between A and B, which might sound a little bit strange because while B, the magnetic field, does have a direction associated with it, A is an area, and we typically don't think of that as being a quantity that has a direction associated with it. And so the way we will think of the direction there is we will take the loop, which I'm going to draw again at the bottom, and I want you to imagine an arrow pointing away from the loop that is perpendicular to the surface of the loop. So for example, maybe the surface of the loop looks something like this, and an arrow that points perpendicular to the surface of that loop might look something like this. And so if I were to rotate that loop, for example, to look something like this, then an arrow that points perpendicular to that loop might look something like this. And so the angle theta in this magnetic flux equation represents the angle between A and B. Where in this case, when I say the angle between A and B, I'm talking about the angle between the line that is perpendicular to the surface A and the magnetic field B. When the area is measured in meters squared and the magnetic field strength is measured in Tesla, then the magnetic flux is measured in meters squared times Tesla, which is actually a new unit called the Weber, which is abbreviated WB, a capital letter W and a lowercase letter b for Weber. The particular values in Weber of magnetic flux are not particularly important for understanding what's happening in this video. What's more important is understanding what causes a change in magnetic flux, because really it's a change in magnetic flux that produces the current that you've observed in the ammeter. And this, what I've stated, is exactly what Faraday's law is. Faraday's law states that a change in magnetic flux, which could be written as maybe delta phi b, a change in magnetic flux induces an EMF in a conducting loop of wire. And the magnitude of that EMF depends on the rate of change in the magnetic flux. And the way that we can summarize this is by writing the EMF produced, which is written here as epsilon, is equal to delta phi b over delta t. And this equation, again, represents Faraday's law. So once again, if you have a conducting loop of wire, like we have with the solenoid, and in that conducting loop of wire there is a changing magnetic flux, then that changing magnetic flux will produce an EMF, epsilon, in that conducting loop. The EMF that's produced in that conducting loop will cause a current, or the flow of electric charge. And so what we are observing is, as I drop the magnets into the solenoid, there is an EMF produced in the conducting wire due to the changing flux, due to the movement of the magnet, and that changing flux is causing you to see a current there. This also should help us understand two other observations that we saw in the first video. And that is, one, when I move the magnet more slowly, the current that is being read by the ammeter is less. If I'm moving the magnet more slowly, the rate of change in the magnetic flux through the coils of wire is less. And this means that the EMF produced by that changing flux will also be less. And if the EMF produced is less, then the current should be less. You should have also observed at the beginning that when I push the magnets into the solenoid, the current spikes in one direction, and when I pull the magnets out of the solenoid, it spikes in the other direction. But when I flipped the magnets upside down, then the current spiked in the opposite direction that it was originally. And the idea of magnetic flux in Faraday's law helps us understand that maybe there's something going on with the polarity of the EMF produced inside of the conducting wire, but it's not enough to fully explain what's happening. And so in the next video, I'm going to introduce a new law, Lenz's law, that will help us understand what's going on with the flipping of the direction of the EMF with the flipping of the magnet.